Yeah, I want to welcome you to my lecture today. This is week 4, lecture 1, as I'm going to be walking you through another exciting topic. Today, I'm actually going to be walking you through probability in our daily lives. The outline for today is actually going to be I'm going to introduce you to probability. We're going to talk about how probability quantify randomness. We're going to work on some the definitional terms using probability. I'm also going to walk you through different kind of views that we have in probability. Then I'm also going to walk you through types of events, and lastly there's going to be examples. So like I said, today's topic is very important because just like what I told you the other time, every research has statistical input, okay, particularly when data are involved. And if it has statistical input, you actually the idea of statistical, you know, the idea of statistics will actually be used. And then when you're using the idea of statistics or statistical models, okay, are probabilistic models. Okay, so and that is the reason why today's topic is very important because the randomness that we talked about the other time. Like you remember the last time uh, I was walking you through uh, you know survey and experimental these studies and stuff like that. Of course, I told you that experimental studies, you know, is you know more preferable to the observational study because it allows randomness. Okay, it allows researchers to be able to randomize subjects to different kind of group. So probability is just a measure to quantify the randomness that we talk about. So, and that is the reason why I'm actually going to be walking you through the concept of probability as it is used in our daily life. Okay, uh, in an hospital, if a physician or a doctor should say that a patient has a 50-50 chance of surviving a surgical operation. So what does it mean? By 50-50 chance, it's trying to say, the patient actually have halfway in making it. And the reason being that, you know, we find ourselves in a world that is stochastic in nature. You know, there is nobody who is sure, 100% sure of what is going to happen next. Okay? In that situation, the event of surviving, the surgery, the probability, the chance of surviving that surgery is out of 100. What the doctor is trying to say is a 50 out of 100. Okay. So, and why does he have to, to say that? Because he has, studied situations and we realize that the situation is dicey in terms of survivor after the operation. Okay, so if another physician should say that, okay, a patient stand 95% of having a particular disease. Of course, having 95% of having a particular disease, he's trying to say 95 out of 100, and he's trying to give room for error of 5%, as there is nothing that is entirely sure and unsure. And that's why I'm actually going to say we find ourselves in the middle of sure and unsure. I'm going to say that again. We find ourselves in the middle of unsure and sure. Okay? So, what I'm trying to say in essence is just like we have something like this, and this is unsure. Okay? And what I have here is sure. So this is where we find ourselves. We used to find ourselves in between. Okay, because there is nothing that is totally unsure in life, and there is nothing that is totally sure. Okay, and that is why, you know for us to be able to quantify, the degree of belief, we use probability value. And of course, when you use probability value, we're actually using probability statement. Okay. Uh, the next thing I'm actually going to talk about is the use of probability. But before I go into the use of probability, what do we actually understand by probability? Okay. I just want to say that the probability, is a measure of doubt. Okay. Is a measure of doubt about the occurrence, okay, of an event, just like mathematical, uh, you know, way of examining the likelihood of the occurrence of an event. For instance, uh, if I compete in an election, what is the probability that I'm actually going to win? I apply for a mortgage loan, what is the probability that I'm actually going to be given? Because we know the possibility before even the occurrence of events. Okay, it's either I was granted the the loan or not granted. Okay, before we go into that, we know possibility, but the fact that we are not too sure of the event that will occur at the end of the day, what is the probability that if I go into a business, I'm actually going to record profits? Of course, I know in the sample space, the list of possible things that can occur is either I make a profit or loss. Okay, so that is what we mean by probability. So probability is a measure of likelihood occurrence of an event. So which means event could occur and events may not occur. Okay? And that is the reason why we actually need to study situation, to be able to have an assurance, okay, to a certain degree, okay, about the occurrence of an event. So the uses of probability. Of course, using probability, of course, you can actually find a chance, you determine the chance of winning the lottery. Like if I actually partake in a lottery, if anyone partake in a lottery, what is the probability that you're actually going to win? You are not the only one. If you are the only one that partake in that lottery, of course, the probability is going to be one. But the fact that you are not the only one that partake in it, of course, the probability is not going to be one. It's going to be sure. Okay, and that is the reason why, you know we can actually compute probability. When you have a probabilistic view of the situation. So I said we can find the likelihood that an employer drug test correctly detects whether or not you have used drugs. I could remember, like in this country, if you are actually looking for a job, I think part of the recruitment process is that after everything is fine, then you need to do a drug test. They're going to conduct a drug test on you. Now, the question now is, if they conduct a drug test on you, what is the probability that if you have used a drug test, okay, their equipment will detect that. I'm going to say that again. What is the probability that if you have used drug in the past, and this particular company actually conduct a drug test for you, what is the probability that the machine they are using or whatever equipment they are using will actually detect that? And what is the probability that if the equipment actually, uh, suggested that, you know, you have used drug, what is the probability that you actually use drug? Okay, because we find ourselves in a world where we don't also expect the efficiency of a machine, okay, or any equipment to be 100%. Okay, and that was why I said there is nothing sure in this world. There is something that we call sensitivity. There's something that we call sensitivity. Okay, there's something that we call sensitivity. Okay, so we call it sensitivity. Sensitivity is actually talking about the proportion of those who have the disease, okay, and tested positive. Okay, the proportion, which means it is not everyone that have the disease that will test positive. The fact remain that the efficiency of the machine is not 100%, and that is the reason why why it happens like that. The efficiency of a machine is not 100%. Okay, so and there's something that we also call specificity. You know, the proportion of those who tested who do not have the disease and tested negative. Okay, the proportion of those who do not have the disease and tested negative. Okay, so as we have specificity, we also have sensitivity, sensitivity. So like I said, the sensitivity actually referring to the proportion, okay, of those who have the disease and actually tested positive. So we can now actually rule out this in life. What is the probability that somebody is being tested for COVID? Okay, and this person actually have COVID. Okay, the person actually have COVID, but the machine was not able to detect that. Or what is the probability that, okay, somebody do not have COVID, and the equipment detects that the person have COVID? Okay, so like I said, there is nothing that is sure in the world, and there is nothing that is unsure. I'm going to say that again. There is nothing in the world that is unsure, totally unsure and totally sure. So, and that is why I said we find ourselves in the middle of unsure and sure. Okay? Okay, so if that is the case, then another thing that we can also talk about. So, like I said, we can measure the uncertainty that comes with randomized experiment and with the random sampling in survey. Okay, so like I said, in my last lecture, where I was trying to walk you through, so sampling survey and uh, that we use observational study and then the experimental study. Of course, in experimental study, we randomize subjects, okay, to different groups, to control group and to treatment group, okay, which I call the experimental group. So what is it? And uh, the randomization is being used by researcher, to assign subjects into two different into the groups, okay, under investigation. What is the probability, okay, that a particular participant will actually ended up in a particular group? Okay, so like I said, probability can actually be used to quantify randomness. Okay, Then even if I'm conducting an observational study, or where maybe I want to actually or I'm conducting an sampling survey where I actually want to select people at random, okay, from the target population, going by what I explained to you before. If I want to take a sample from the target population, of course, and I use instruction of chance, okay, where there is no favoritism or biasedness in my selection, so which means it's purely random, okay. So how can we quantify that randomness? Of course, probability can actually be used in that regard. Okay, so like I said, how to, how probability quantify randomness. Of course, statisticians, researchers actually rely essentially, on essential components that we call randomness to avoid bias in gathering data. Of course, that was what I just talked about. Okay, in order to eliminate bias, so what we actually do is to use principle of randomization, okay. And if you really want to know how this randomization can be quantified, okay, so probability actually can be used to quantify randomization. Okay, so and not really that, randomness also applies to the outcome of a response variable. Okay, if I want to predict a particular response from a predictor, for example, maybe I want to predict you know, uh, the volume of sales, okay, from the amount of advertising, okay, from advertising, okay. Advertising is my predictor. The amount I spend on advertising is my predictor. And of course, my response is the volume of sales. Of course, the volume of sales is assumed, the response is assumed to be random. Why is it random? It's random because of the fact that the statistical model we're actually going to use have two components. Okay, the statistical model that we're actually going to use have two components. Okay, we got a deterministic component and we got what we call the random component. Okay, we got a deterministic component, we got a random component. Okay, and because of that, okay, the response variable is now subject to variation. Okay, because the way we normally have that, for instance, if I'm talking about simple linear regression model where I'm looking at the effects of I'm looking at the effect of a predictor, okay, on X is my predictor right here, and Y is my response. Okay, S is my predictor, and Y is my response. Okay, so the deterministic part of the model is this guy here, and this is error. Error is a random part of the model. There's always going to be error. There's always going to be a random part in any statistical model. Okay, there's going to be random parts in any statistical model. Okay, now because of the random part, and that is the reason why statistical model is probabilistic in nature. I'm going to say that again. Because of the incorporation, because of the inclusion of random parts, the random component into statistical model, and that is the reason why statistical model is probabilistic in nature. Okay, so as a result of that, the response variable that we actually want to predict, given the predictor, in this case, I'm calling the predictor X, okay, that response variable will be subject to variation, okay, will be random, okay, and that is the reason why I said randomness also applies to outcome of a response variable, okay, and you know what, the probability will enable us to quantify the randomness, okay, because we actually need to quantify that randomness. Why do we need to quantify randomness? We actually need to quantify randomness because assumption there are assumptions on imposed on any statistical model, and the assumption that is imposed on any statistical model is actually centered on the random component. I'm going to say that again. Assumptions imposed on any statistical model actually centered on the random component. Okay, now in the subsequent lecture, I'm actually going to be walking you through what we call regression analysis, and so on like that, cause and effect model, where maybe you actually want to predict one variable from the other one, or you actually want to test that a significant difference, between treatment of different group. When you really want to do that, we always have we have assumption, okay, and the assumption actually centered on the error, okay, which is centered on the random part, okay. And you know what? Those assumptions, talk about one of them talk about the probability distribution of the random components. That is the probability distribution of the error term. Okay, so in a way, that will enable us, knowing the probability distribution of the error time, will enable us to quantify the randomness that we talk about. Okay, so these are what I'm actually going to walk you through in the subsequent lecture. Okay, so all what I'm just trying to tell you right now is how probability can actually be used to quantify randomness. Okay, so mathematically speaking, if we want to define probability, now let me tell you this: we live in a stochastic world. We live in a world where different things are happens in different days. Okay, there is no human being who have a perfect understanding of what is going to happen next. And do you know why that? Do you know uh, why we have that? Because there's a variation in the world. Different things that happens in different days. Okay, those who are into business, okay, all days are not the same in business. There's going to be some days where the business is actually going to boom. There's going to be some days, where there's going to be a kind of recession in business. Okay, so which means we got different occurrences. Okay, and you know what? Despite the fact that we got different occurrences, there's variation. We always have a certain outcome in mind. Okay, like somebody who is going for an election is going to compete in an election. Of course, uh, what he has in mind is, the event of winning. Okay, that's what he has in mind. But you know what? It is not only event of winning that can occur in life. Event of losing can also occur. So somebody who is doing business, okay, I know what the person have in mind. Every business person, actually, have a profit making in mind. But you know what? It is not only profit that exists in this world. When you talk about business, okay, there could also be loss. Okay, and that is the reason why when we're talking about probability actually thrive in variation. If there is no variation, then there is nothing like probability. I'm going to say that again. If there is no variation, okay, there is nothing like probability. I'm actually going to write that down right now, okay? You know, like I said, okay, no variation, okay, no variation, okay, no probability, okay, no variation, no probability. Everything is the same, okay? If the same thing happen in different days, okay, then there's nothing to worry about. No probability in that situation. Everything, because in a situation where the same thing happen in different day, then it means you have only one state of nature. Okay, you have only one state of nature. Okay, one state of nature. And you know what? We live in a world where there is more than one state of nature. Okay, we live in a world where there is more than one state of nature, and that is the reason why you don't really expect That's why we need to find probability of the occurrence of certain characteristics of interest. Okay, so I'm going to give you an example from politics right now. Um, in the United States of America, the number of senators, they are 100, because each state in the United States actually they have two senators that are representing them in the House of Senate. Okay, now if I'm interested in the number of females, okay, in the Senate House of the United States, okay, then it means, of course, which means by gender, there's a variation by gender, because they got females, they got males, okay. So if I want to talk about the probability of female, okay, female senators, okay, of course, uh, I'm actually going to, I need to first consider possibility. Okay, the possibility is actually going to be, what is the sample space, okay, what is the size of the sample space. Okay, the size of the sample space actually going to be the totality. Okay, like how many senators do we have in that, 100 senators. Okay, what is the characteristics of interest? Okay, how many females? Okay, so the probability of female, okay, is going to be the ratio of the number of females to the totality of the senators. Okay, and that was why I said, if I have n mutually exclusive and equally likely ways, okay, and if small m of these possess a trait, okay, the trait that I'm talking about is the characteristics of interest, okay, then the probability of the occurrence of E is actually going to be the probability of E equal to small m divided by big N. Okay, so which means the ratio of the characteristics of interest, okay, to the totality. Okay, that is what we mean. That is how mathematically, that is how to define probability. Okay, what you're actually going to have at the bottom. Okay, so what you're going to have at the bottom, the big N here is going to be talking about the totality. Okay, and what you have at the top, okay, is actually going to be talking about the number of the favorable outcome, or the number of events of interest. Okay, so that is what that is actually talking about. Okay, so that is the mathematical definition of probability. Okay, the next thing I'm actually going to talk about now, I'm actually going to walk you through definition right now. We're going to talk about some terms using probability. I'm actually going to start from experiments. Okay, when I say experiment, I'm not talking about, I'm not only talking about, you know, the experiment you perform in the lab. I'm not only talking about that. Okay, when I talk about experiments, okay, is an act of performance. Okay, anything at all, any a trial is a trial that generates an outcome. We find ourselves in a world where we got a lot of trial. Okay, and of course, when you have a trial, we're always going to have an outcome. Okay, now, uh, but we have certain outcome in mind. Okay, we have a certain outcome in mind. Okay, like a student that is writing an exam, that is under trial. Okay, at the end of the day, there's going to be an outcome. Okay, and you know what, before go into that exam, okay, you already know possibility. Okay, what is the possibility? Is either it's going to pass or fail. But you know what, we don't know the exact outcome, you know that's the nature of the outcome that will occur at the end of the day. But before we go into research, we already, before we go into a trial, we know the possibility. A business person, before going into business, of course, he or she knows that, okay, in his or her sample space, is either a record profit or loss. Okay, a politician, somebody who is competing for an election, okay, no possibility. It's either he win or loses, okay, but only that at the end of the day, he doesn't really know what the outcome is going to be. Okay, it does not really know what the outcome is going to be, but he know the possibility. Okay, and that was why I said, experiment consists of a number of trials. Okay, under the same condition. When I try, uh, this time, what did I get? Just like I got a coin. Okay, there are two sides in a coin, right? Got head and tail. Okay, so when I flip a coin, okay, so I'm actually going to observe the side that show up. And maybe before taking a coin, maybe what I have in mind, okay, I want an head to show up. Okay, there's possibility that if I toss a coin, I may not even see what I'm looking for. Okay, I could remember Ralph Emerson. Ralph Emerson was one of the wisest one of the wisest men of his time, of his generation in the United States of America. Ralph Emerson performed experiment one time, no result, second time, no result, third time, no result, 99 times, no results. And when he now performed the experiment the 100th time, he had a result. Now, a group of scientists actually called, organize an occasion to celebrate Ralph Emerson, for his breakthrough, after so many failed attempts. So I could remember, the person that was introducing Ralph Emerson, said, and I quote, uh, then Dr. Ralph Emerson said, Dr. Ralph Emerson, on behalf of my fellow scientists, I will sympathize with you, you know, for for taking for so long before you could get a breakthrough in your research. But do you know what Ralph Emerson said in response? Ralph Emerson said, "You don't need to sympathize with me." He said, "Now I know 99 ways of how not to approach a situation, and I only know one way of approaching a situation." I'm going to say that again. Ralph Emerson responded by saying, "Now I know 99 ways of how not to approach a situation, but now I only know one way how to approach a situation." So I think the takeaway from Ralph Emerson is just that, okay, when I'm trying to, I'm making an effort to get something done, and I don't get it done. Maybe I'll be in the first trial, second trial, and so on like that. We don't need to give up. We're going to continue struggling. We're going to continue until we figure that out. Okay, so I think Ralph Emerson was trying to, he tried to display what I call spirit of endurance, spirit of perseverance. That was what he displayed. And at the end of the day, he had a breakthrough. Okay, so what I'm trying to talk about at times, probably in business, you are actually recording loss. Don't give up. You just need to make sure you know you strategize and be more focused, and before you know, you're going to be recording profit, in manifolds. Okay, so so that is what we mean by experiment, and I also call a planned process of data collection. Okay, now I've been talking about sample space. The other time I said you want to go into a trial. Okay, you want to perform an experiment, you want to go into anything that actually generates an outcome, but you already know possibility. So when I talk about sample space, the sample space means the collection of possibility. Okay, the collection of possible outcome, in an experiment. Okay, that's what we call sample space. So if you want to answer any probability question, then you need to be able to have an advanced knowledge of the sample space. Okay, you need to understand what is the possibility. Okay, what are the possible outcomes that can actually have uh, in the you know in this experiment. Okay, even before the experiment are performed. Okay, then there's something we call simple events. Okay, so we may have a sample space of of outcomes. Okay, and we may be interested in a particular uh, outcome. I'll take a look at what I'm trying to showcase right now. Okay, where we have male, female. Okay, of course, a male is a simple event. Female is a simple event. Okay, it now depends on, you know, the characteristics of interest. Okay, so, and that was why I said, when I talk about sample space, of course, uh, we're gonna it's gonna be like a collection of distinct objects. You can see male is different from female, and you know what? All the events in the sample space, for you to have a very nice sample space, events have to be mutually exclusive. Okay, I'm still going to talk about event being mutually exclusive and being mutually exhaustive. Okay, and you know what? You should the sample space should be a set, that contain distinguishable items. Okay, okay. Now the next thing I want to talk about right now is what we call the complements. Okay, for instance, when I give me 1 second. I think uh this should be okay. Yeah, a complement. Yeah, that's a complement. Yeah. Okay, so when I talk about complement, okay, if I'm considering a particular event, for instance, I'm going to give you this example. Okay, let's say if I happen to be a businessman, of course, you know, in my sample space, it's either I have profit or loss. Okay, now profit and loss actually constitute my sample space as a businessman. Okay, that means I got those two events. Okay, now if I'm talking about the complements of loss, of course, the complement of loss will automatically be uh, profit. The complement of profit automatically be loss. So when I talk about, the complement, okay, the complement is more or less like, okay, the event I'm not interested in the sample space. Okay, if I talk about, if I'm interested in event A, okay, then the complement of A would be the event I'm not interested in, because it's not possible that I'm going to be interested in all events in the sample space. Okay, I'm not going to be interested in all of them. Okay, so if I need to, that means I need to identify what I'm interested in, event I'm interested in. So the complement of that is the event that I'm not interested in. Okay, and you know what? Complement, we can use this to denote that a bar, and at times, we could write a complement, a c, like that. Okay, and if you take a look at what I have right here, since event that I'm interested in and the one that I'm not interested in constitute the sample space, then when so which means it's either I have the event I'm interested in or the one I'm not interested in. Okay, in business, it's either I record a profit or I record a loss. In election, it's either I win an election if I partake in an election or lose an election. Okay, so which means it's either this or that. Okay, and there's possibility that there could be more than two. There could be so many events. If I'm interested in one, I'm not interested in the rest. Okay, now in that case, the probability of of the event that I'm interested in plus the probability of the event that I'm not interested in must be equal to 1. Okay, so the one here is it's the same thing as the probability of a sure event. Okay, it's the same thing as the probability of a sure event, because the probability of a sure event equal to 1. Okay, why is that? Because the if I have two events in a sample space, okay, event A and the complement of A, okay, so it's either I have A or I have the complement of A. Because I'm using or, then if I want to talk about the probability of getting A or its complement, I'm actually going to add the two probability together, and that must give me 1, because event A and its complement are mutually exclusive. Okay, so what do we mean by mutually exclusive? Okay, I'm actually going to walk you through that. Okay, as time goes on. Okay, so mutually exclusive is trying to say it's either this event occur or the other one occur. You know, they can occur together. Okay, there's nothing like a joint. Okay, now the next thing that I actually want to walk you through right now, what are the views in probability? You know, we got different school of thoughts in probability. Okay, the very first thing I want to talk about is what we call subjective approach. What do we mean by subjective approach? Now, what we mean by subjective approach is just, is an estimate, okay, that actually reflects, a person's opinion or best guess about whether an outcome will occur. You know, at times we use experience to be able to tell about the probability of the occurrence of an event. Um, what the subjective approach is trying to tell us is that events in my sample space, events in sample space, uh, are are not equally likely. Not equally likely mean that some events have a greater chance of occurring than others. I'm going to give you an example right now. Uh, you know, uh, be- uh, because I'm not a professional boxer. If I should go and if I should go and compete a professional boxer, okay, I'm not a professional boxer, and I actually want to compete with a professional boxer, okay, maybe like Mayweather or Iron Mike Tyson or Anthony Joshua or and the like. Of course, you all know the result even before the fight, because I'm not a professional boxer. The probability that I'm actually going to win is actually going to be very, very small compared to those who are professional boxers. Okay, so with that, that's a subjective approach. Subjective approach is just using past antecedents, okay, to judge the probability of the occurrence of an event. Okay, so it's not giving it's not going to give an equally likely situation, okay, to the item in the sample space. Okay, and you know what? Subjective approach is very useful in medicine. Okay, and that was why I said, it formed the basis, okay, of a physician opinion based on information gained in the history and physical examination about whether a patient has a specific disease. Now, uh, we don't expect physicians to have an empty mind, but they need to be experienced for them to be able to know, whether a particular patient have a disease or not. I could remember, when I go to hospital, the doctor is going to touch your body, they're going to, by the time they touch your body, they look at your face, they check different kind of stuff. From the experience they have, they will be able to they recommend an appropriate test. Okay, so which means they are actually using what we call a judgmental approach. They are using a subjective approach. They are being, because they need to have the best intelligent guess about what could happen. Okay, so that approach is called subjective approach, and of course, it's very, very useful in medicine. And not only that, right now, candidates are, the election is coming up, in the United States in November. And of course, there have been some opinion poll, conducted by different kind of organization, okay, about, the chance of a particular candidate. Okay, of course, when you watch CNN, the Fox News, the MSBC, and and stuff like that, you can track some predictions. Okay, and so with that, they are trying to use kind of subjective approach, arriving at that. But let me tell you something. Like I said, there is nothing in life that is totally sure, and there is nothing in life that is entirely unsure. Okay, so what we normally do most of the time, we find ourselves in the middle. Okay, Now, the next approach is what we call classical approach, okay, which is more or less objective, okay. So when we're talking about classical approach, the classical approach will actually go against the subjective approach. Don't forget, the subjective approach actually assume elements in the sample space are not equally likely. But the classical approach believe that elements in the sample space are equally likely, that there is no element with a better chance or probability of occurring than others. Okay, that is what classical approach is talking about. Of course, this applies to a coin. When you flip a coin, there are two sides in a coin. Okay, head and tail. Okay, and the probability of any of the sides showing up is going to be one over. The probability of a head showing up is going to be one over two. The probability of a tail showing up is going to be one over two. But you know what? That is a theoretical probability. Because the theoretical probability, of course, is going to tell you, okay, when I have a die, when I have a coin, the probability of head showing up is going to be 1 over 2. The probability of a tail showing up is going to be 1 over 2. But what of in a situation whereby I take on a coin right now and I decide to experiment by trying, I don't want to rely on theoretical assumption that give 50-50 to the side. If I toss a coin first time, maybe I see head, second time head, and I toss it 10 times, and I probably observe 7 heads out of 10 trials. Of course, in that situation, the probability of head showing up is going to be 7 over 10. It's going to be 7 over 10 as against, it's going to be 7 over 10, because when I toss it, okay, I toss it 10 times and I see 7 heads, okay, out of 10 trials. Then the probability is going to be 7 over 10. And that is actually going against. That is not equal to 5 over 10 proclaimed, theoretically. Okay, the theoretical assumption is that, okay, because it's a one of, the probability of any side showing up is 1 over 2. Then if I toss a coin 10 times, I should have 5x out of 10. I may not have 5x out of 10. I could have 7 out of 10. If I have 7 out of 10, then in that situation, experimental probability is actually going against theoretical. But you know what? On the long run, when I continue to have a good number of trials, okay, the experimental probability will actually converge to the theoretical probability. So like I said, the experimental probability will converge to the theoretical probability. Okay, and that was why I said if a coin is flipped 10 times, there's a guarantee that exactly 5 will be observed. Okay, and there may not be guaranteed that you flip that 10 times, there may not be guaranteed. But if you flip so many times, then at the end of the day, you're going to have the probability of a side showing up converging to the theoretical one of a 0.5 that I call 1 over 2. Okay. Now, the next thing that I want to talk about right now is what we call relative frequency. And what do we actually mean by relative frequency? Of course, what we mean by relative frequency is just going to be the ratio of the number of times favorable to the experiment to the number of times an experiment is performed. Okay, and of course, that is where we derive the mathematical definition of probability, okay, as a ratio of the number of occurrence favorable to the experiment to the number of times an experiment is performed. Okay, so uh, let us assume that we have data set right now. If you take a look at what I'm showing you right now, so what I'm showing you right now is a data, collected across gender and across blood group. Okay, we're actually going to make use of this data. Okay, when you're figuring out probability. And let me tell you something. if we have the same blood group in this world, then we don't need probability. If we have the same gender, okay, in this world, then we don't need to worry about probability. But you know what? When you collect data from inquiry, from the field of inquiry, from the population of interest, and you actually ask something like this, of course, we may be talking about probability. Okay, what is the probability that I'm actually going to choose female? What is the probability I'm going to choose male? What is the probability I'm going to choose somebody that have that belong to blood group O or blood group A and so on like that? Okay, so because of the variation like this, of course, we can actually determine probability. Okay, so there's something that we call marginal probability. And the marginal probability is just trying to call, we're trying to figure out the probability of a single outcome. If you take a look at what I have in this table, two variables, gender and blood group. Those are the two variables here. Okay, gender has two levels, male and females, and blood group has four levels. Okay, blood group O, blood group A, blood group B, and blood group AB. Now, if I want to talk about marginal probability, it means I'm interested in a particular variable. Don't forget, in this table, I got two variables, blood group and gender. Okay, by marginal, okay, it means I'm actually want to sacrifice the other variable. Then I want to focus on one variable. Okay, and if I want to focus on one variable, I'm actually going to, consider, one level within the variable. Okay, now, and if you take a look at the example right here, what is the probability of, male? What is the probability of a blood group A? And of course, if I want to know the probability of male, of course, it means what is the number of male and what is the totality? Okay, if you go back right here, you're going to see that the number of male here is 50. Can you see that now? That is the number of males, and this is the totality. Okay, 100 is is like the sample size. Okay, that is the sample space. Okay, so if I want to find the probability of male, then it's going to be the ratio of number of male to the totality. Okay, and that is the reason why you have 50 divided by 100, and that gives us a 0.5. Okay, you need to reduce that. And I also want to tell you, uh, you can actually, you know, uh, you can, if you want to present probability result, you can present probability result in terms of fraction. You can present probability result in terms of decimal. Like what I have here now is in decimal. Okay, so what I have here now is in decimal. So you can have it in terms of decimal, and you can also have it in terms of percentage. Okay, in terms of percentage, of course, if I multiply this by 100, okay, and that will actually give me 50%. Okay, so that is telling me that 50% of male, okay, 50% of the population, the 50% of the respondents are males. Okay, so that is what that is actually talking about. Okay, now the next thing I want to talk about now, you can determine the probability of a blood group A. If you want to determine the probability of a blood group A, okay, you're going to look at it. What is the totality of the respondent that have a blood group A? Okay, if you take a look at the totality of the respondent that have a blood group A, you're actually going to see that there are 35 of them. Okay, there are 35 of them. Look at that. So 35 of the respondents actually have, they belong to blood group A. So the probability of a blood group A will actually going to be the number of people with that blood group A divided by totality of the sample space. And of course, in that situation, that's going to give me 35 divided by 100. Okay, that can actually reduce. Okay, can reduce 5 goes there. That will be 7 divided by 20. And of course, in fraction, in decimal, that is going to be 0.35. And of course, that's going to be 35%. Okay, So that is how you can actually figure that out. Okay, so give me 1 second. I'm going to erase that right now, and I'm actually going to move to the next slide. Okay, so let's now talk about the properties of probability. Of course, the probability lies between 0 and 1. Okay, line ranges between 0 and 1. Okay, so the highest value you can get is 1, the lowest value you can get is 0. Okay, and of course, if an outcome cannot occur, then we say the probability is 0. Okay, and if an outcome is sure, then that has a probability of 1. Okay, the probability of a sure event is 1. The probability of the event is not going to occur is actually going to be 0. Okay, and the sum of probability of mutually exclusive outcome is actually going to be equal to 1. If I have male and female in a population, the probability of male plus probability of female will be equal to 1, because male and female are mutually exclusive. And you know what? They are also mutually exhaustive. Okay, they are mutually exhaustive because they constitute the population. So therefore, if I pull male and female together, that give me the population, and of course, the probability of the of the sample space is more or less the probability of a sure event that's actually going to be equal to 1. And equal to 1, what I'm trying to talk about, if I wanted to say that in a probability framework, it's actually going to be called 100%. Okay, which means I'm talking about the whole population. Okay, so the next thing that I want to talk about right now is talking about different kind of events that we have, because you know what, probability are associated with events, and that is the reason why you need to be able to understand, what are the different kind of events, because a particular probability value, formula that you're actually going to use depend on the event we're talking about. I'm going to say that again. If you are given probability question, okay, if there's a probability problem, you need to be able to understand what is the corresponding event. Okay, what is the event in that question? Okay, if you understand the kind of event in that question, and that will enable you to, to apply appropriate probability formula. Okay, so and that is the reason why I actually want to walk you through on different kind of events that we could have. Okay, because there's a probabilistic implication for different kind of events. Okay, so the first event I'm actually going to talk about is a mutually exclusive event. What do I mean by mutually exclusive events? You know, if I want to talk in the framework of two events, A and B, okay, event A and B, of course, are mutually exclusive if and only if they cannot occur together. Okay, they cannot occur together actually means it's either one occur or the other one occur. I'm going to say that again. It's just like, I compete in an election. It's either I win or I lose. Okay, I can't win and lose at the same time. That's not going to be possible in the same election. Okay, and in the same business deal. Okay, for a particular business deal, I can't record a profit and say record a loss at the same time. So in a situation where that occur, okay, then that kind of event can be called mutually exclusive event. So in other words, we're trying to say the occurrence of one event will prevent the occurrence of the other one. Okay, the occurrence of one event will prevent the occurrence of the other one, and what that implies is that the two events, they cannot occur together, they are actually disjoint, and that's exactly what I'm trying to show right here. Okay, where A is occurring separately, or B occurring separately. And you know what, if events are mutually exclusive in such a way that it's only one that can occur, okay, then this will attract addition rule in probability. Okay, when you're talking about mutually exclusive events, okay, with situation where event cannot occur together, is either one occur or the other occur, then that will attract additional rule. Okay, and you know what, the symbolic representation, okay, the set notation for that. If I want to find, okay, it's either A or core or B or core, then the probability of either A or B or core, then it's going to be A union B. It's going to attract union. And you know what? And that is the addition of the two probability. So I can only talk about using the addition of probability, in a situation where events are mutually exclusive. Okay, so you need to be able to know. So when you identify a problem to be mutually exclusive, okay, if you really want to figure out the probability of an event occurring, of course what you need to do is to add the two probability, just to add the respective probability of the event. Okay, so like I said, mutually exclusive will attract additional rule in probability. Okay, so I want us to use that same question, you know, the problem that I showed the other time, this table. So I want us to make use of this table. And how can we use this table to answer a question that has to do with the non-mutual, that has to do with the mutually exclusive? Okay, how can we actually do that? Of course, let's look at the question. How does, a question under mutually exclusive look like? And that is why I'm asking this question right now. Said the probability of being either blood type O or blood type A. Maybe they want you to figure that out. Of course, you cannot, you know, you can't belong to blood type O or blood type A at the same time. It's either you are there or there. Okay, so the probability of you being either blood type O or A, then it's going to attract union. Okay, like I said. Okay, so then I'm actually going to add the two probability together. Okay, so this guy here is the probability of a blood type O. Now that means if you go back to the table, okay, how many people do you have? That's going to be 40. Okay, in the blood type O divided by 100, and that's going to be the probability of a blood type O, which is 40 divided by 100. Okay, and for the blood type, you know, for the blood type A, then you're going to figure out the number of that. You got 35 of that divided by 100. Then you're going to add the two. Then the 0.75 is the probability of whether you belong to blood type O or blood type A. So what I'm just showing you right now is an example of a mutually exclusive event. And of course, this attracts additional rule. Okay, situation where you needed to add the two probability. Okay, this is another question. In a normally distributed population, the probability that a subject's blood cholesterol level will be lower than one standard deviation below the mean is 16%. And the probability of being blood cholesterol level higher than two standard deviation above the mean is 2.5%. Okay, what is the probability that a randomly selected we have a blood cholesterol level lower than one standard deviation below the mean or higher than two standard deviation above the mean? Of course, based on this is mutually exclusive, because it's either you have one standard deviation below the mean or you got two standard deviation above the mean. So in this situation, you're actually going to add the two probability. Of course, the first probability given here is 16%, and the second probability here is 2.5%. Don't forget that I told you probability can be presented either in percentage, in decimal, or in fraction. Okay, so in this situation, if I want to find the probability that a randomly selected subject will either have once we have a blood cholesterol level lower than one standard deviation below the mean or higher than two standard deviation above the mean, then I'm actually going to add it together. Okay, I'm going to add the two probability together because it's either that or that. And don't forget that in a situation where we have stuff like this, we need to add the two probability. Okay, so the next event that I want to talk about right now is a non-mutually exclusive. The other time we talk about mutually exclusive, but right now we're talking about non-mutually exclusive. Okay, so when we talk about non-mutually exclusive event, okay, a non-mutually exclusive event is either, like, if I want to give an example, if I want to base it on just two, if I want to speak in the framework of two events, okay, it's either A occur or B occur or both occur. I'm going to say that again. It's either A occur or B occur or both occur. Okay. Now, if you take a look at this, that is the reason why you can say A can occur separately, B can occur separately, and they can both occur. So in that situation, this is going to attract, a different rule. Okay, this rule is what we call principle of inclusion and exclusion, because I'm still talking about probability of A or B, but I'm still talking about union, and only that the only difference between the formula that I want to write right now and the one I've written before, I'm actually going to be subtracting their interception, okay, from the total. Okay, when you take a look at this side is mutually, but when you take a look at all of that, when you're subtracting this from that, it become non-mutually. Okay, so I'm going to give you an example right now. If uh, for instance, uh, maybe there are two mailing, maybe delivery, maybe for instance you order for burger, maybe you order, to buy something from my burger, and you order to buy another something from probably Burger King. Okay, and then of course of course uh, you're actually using different delivery service. Now the question now is, what is the probability that you're actually going to get your order on time? Of course, the probability that you're going to get your order on time is this. It's either you get the order from my burger on time, or you get a burger from the Burger King on time, or you get a burger from, both on time. Okay, so in that situation, it's going to be non-mutually. Okay, and this is an example. Okay, I still want to use that table. Okay, that table of problem, and take a look at this question. It said two events are not mutually exclusive. For instance, what is the probability that is actually going to be a male, okay, or belong to blood group A or blood group O? If you take a look at what I have here, what is the probability, okay, that when I choose somebody from that respondent, okay, uh, the person is actually going to be male, or it belong to blood group O. And let me tell you something. Somebody can be male, okay, and we have people that belong to blood group O, and we can have a situation whereby a male belonging to blood group O. That is not mutually. I'm going to say that again. Event of male can occur, event of can occur separately, event of being belonging to blood group O can occur separately, and an event of being a male, okay, and belonging to blood group O can also occur. Okay, so in that situation, this is what I'm actually going to use. Now the question is, what is going to be the probability of male? Of course, I'm going to go back to the table, and the probability of male is actually going to be 50 divided by 100. Okay, and what's going to be the probability of a blood group O? And that's going to be 40. Okay, 40 divided by 100. Then what is the probability of a male? Okay, what is the probability of a male, okay, belonging to blood group O? Now if you take a look at that, this is a male belonging to blood group O. Of course, I'm actually talking about this guy here. Okay, so if I want to look at the probability of male intercept blood group O, it's actually going to be 20 divided by 100, and that's going to be 0.2. Okay, that is the probability of a male okay, belonging to blood group O. And this is what I'm actually going to subtract. Uh, this is what I'm actually going to, that's exactly what I'm trying to, that's what we're trying to do right here. Can you take a look at that? Okay, that's what I'm trying to do there. Can you see now? So at the end of the day, so what I've applied here is non-mutually. Okay. Okay, so the next thing that I'm actually want to do now is to go into another event that we call independent events. Okay, so when we talk about independent events, what do we mean by independent event? You know, two events are said to be independent if and only if they can occur together. Okay, the occurrence of one does not affect the other. Okay, so when I have a die and I have a coin, the occurrence of any side in a die cannot prevent the occurrence of any side in a coin. Okay, since I'm tossing them together. And you know what? In a situation where that occur, that way attracts a symbol, that way attract a multiplication rule. Okay, that will attract multiplication rule. It means I actually need to multiply the two events, the probability of the two events. Okay, I can only multiply the probability of the two events if and only if events can occur together. And that was why I give an example: landing on head from two different coins. Okay, rolling a 4 on a die, then rolling a 3 on the second roll of a die. So those can occur together, and that will actually attract I mean multiplication rule. Okay, now, and we have conditions for two events to be independent. Okay, so for two events to be independent, of course the probability of A depending on B is actually going to be equal to probability of A, and the probability of B depending on A is also going to be equal to probability of B. And generally speaking, of course, two events are independent if the probability of the joint, okay, can be written as a product of the respective probability. So I'm actually going to show you, how you can actually do that. Now, how can we apply, for instance, if you want to ask a question where we're going to make use of uh, you know, independence. How do we know? Now, take a look at this. What is the probability of being a male and belonging to blood group AB? The probability of being a male and belonging to blood group AB. Of course, that is going to be the probability of male M and AB, and that's going to be an interception. Okay. Now, if I want to get that, what I'm actually going to do, I'm actually going to go to male, go to the table. Now, this is male, blood group AB, male, blood group AB. That's going to be 5, and that's going to be 5 divided by 100. Okay? So this is the probability of the joint. Okay? That's going to be joint between male and AB. Okay? That will be 5 divided by 100. Okay? So that's exactly what we're trying to say. Okay, right here, that is 0.05. So which means 5% are male. And at the same time, they belong to, a blood group AB. Okay? Now, I got further examples that I want to give you. Now, see on the independent events, okay? Like for instance, if a coin is toes and the six-sided die is roll, there are two different things. A coin that have a six side, I'm sorry, a coin that have a two sides and a die that have a six sides. They are rolled together. Okay, find the probability of landing on the head side of the coin and rolling a 3 on the die. Of course, how many sides do we have in a coin? We got two sides. The probability of an head showing up is going to be 1/2. So which is this guy here? Okay, so which is this guy here? And how many sides do we have in a die? 1, 2, 3, 4, 5, 6. What is the probability of 3 showing up? It's going to be 1 out of 6 because we're using classical approach. It's going to be 1 out of 6, which is this guy here. Now, what is the probability that the 2 will show up, what is the probability that, okay, Ed will show up and 3 will show up in a die? Of course, I'm actually going to multiply the respective probability. And that is that's exactly what I'm trying to do right here. Okay, where we have, for the probability of Ed is going to be 1 over 2, the probability of 3 showing up is going to be 1 over 6. I'm multiplying that, and that will give us 1 over 12. So what we are actually applying here are independent, using the knowledge of independent event, because of course we know this event can occur together, because occurrence of one will not negate the occurrence of the other. The occurrence of one will not prevent the occurrence of the other. Since they can occur together, of course, we're actually going to multiply the respective probability. Okay, and this is another example. You can actually read that up. Okay, that's a further example on independent. And this is another example on independent. You can read that up. Okay, now this is very interesting to me. A school survey found that 9 out of 10 students like pizza. You conducted a survey. I walked you through survey the other time. Okay, the principal underlying survey. Okay, and maybe you conducted a school survey and you found out from your study that 9 out of 10 students like pizza. Okay, now if 3 students are choosing at random, okay, with replacements, with replacement mean when I choose the first person, okay, and I ask question on whether he or she like pizza, okay, I actually replace him or her back to the population, okay, before the second person is choosing, okay, in that situation, and then we can the population is going to remain the same, okay. Now, uh, what is the probability that all the 3 students like pizza? Of course, the probability of a student one like pizza is going to be 9 over 10, and that is what we're going to assume for any other student. Okay, that's what we're going to assume, because picking a first person, we actually replace the person back into the population. Okay, so 9 over 10 multiplied by 9 over 10 multiplied by 9 over 10 will now give us the probability that the 3 would like pizza. Of course, when you look at 9 over 10 times 9 over 10 times 9 over 10 will be smaller than 9 over 10, because the more students you have, when you're assuming this probability, after multiplying that, it's actually going to be smaller than 9 over 10. Okay, now this is another example. Okay, if tuberculosis or meningitis had a case fatality of 20%, find the probability that this disease will be fatal in 2 randomly selected patients. Oh, in 2 randomly selected patients. Okay, of course, that is independent. You can multiply the 2 probability. So what is the probability given here? 20%. You multiply 20% by 20. And that will actually give you 4%. Okay, the 4% you are having here, it's saying that when the probability of, when you pick, 2 people at random, the probability that they're going to have that disease is going to be 4 out of 100. That's very small compared to 20%. Okay, so then the second question actually said, if 2 patients are selected randomly, what is the probability that at least one of them will die? Okay, the probability at least one of them, let me correct myself, when I talk about fatality, because what was given here is 20%, it's more or less like a death rate. Okay, so the first one that I talked about the other time, so find the probability that this disease will be fatal. Okay, with fatal is that, okay, choosing any 2 patient at random, just like the probability of dying. Okay, the probability of fatality. Okay, so I'm actually going to multiply 20% by 20%, and that's actually going to be me 0.04, and that will be 4%, and which is smaller down. So which means there's a 4 out of 100 chance that is actually going to occur, that 2 of them, that the 2 patients will die. That's what we're trying to say. But for the second question, he said, if 2 patients are selected random, what is the probability that at least one of them will die? When I say at least one, look at that. Let's reason. At least one. Oh, it's either this person die, or this person die, or they both die. I'm going to say that again. It's either this person die, or this person die, or they both die. That is non-mutually. Okay? That's going to be non-mutually. And that was why you can see the probability of first die or second die minus both die. Okay? So the first die, of course, still remain 20%. Second die still remain 20%. Both die is what I computed here. And at the end of the day, the probability that at least one person is actually going to die would be 0.36, which is 36%. Okay? So that is how that is being figured out. So the next thing I want to talk about is axioms in probability. What do I mean by axioms? You know, axioms are just rules, okay? Rules that guide probability. Give me 1 second. I think I'm going to make this thing to be bigger. Okay. Okay, so when I talk about axioms, of course, I'm actually talking about rules that guide probability. And what are these rules? Okay, because if you really want to apply probability formula, so what are those things you must get? What are those things you must not get? Okay, so if you take a look at if I have if E is an event, okay, and it's a subset of X, S is more or less like a sample space, okay, then the probability of any event will lie between 0 and 1. I think I said that before. And if you take a look at this guy here, okay, if you take a look at that sign is what we mean by empty, okay, we call that empty, okay, that's called empty set, okay, empty set, okay. Now the probability of an empty set, empty set, just like a set that does not have any item in it, okay, and the probability of an empty set is 0, okay, and that's exactly what I'm trying to showcase right here. The probability of an empty set equal to 0, okay. So, and you know what, if the probability of an empty set equal to 0, okay, now in a situation where I'm talking about mutually exclusive, if A and B are mutually exclusive, where it's either A occur or B occur, then it means their intersection, okay, they are not going to have anything in common. So what they're going to have in common is going to be empty, okay, and if what they have in common is empty, then the probability of A intersection B would be equal to 0, because the probability of an empty set is 0, okay? Then the probability of a sample space is equal to 1, because that's a sure event, because at least one event must occur in the sample space. So that's what I'm talking about in number 3. Okay, so I'm going to clean my board right now. I'm going to go to the next slide. Okay, so of course, number 4 is the formula of non-mutually. Number 5 is formula of mutually. And number 6 is the formula to figure out complementary event. Okay, so what is next? What I'm going to, on Wednesday, in the next lecture, I'm actually I'm gonna walk you through on dependent event, conditional event, the total loss of probability, and the Bayes theorem. So I want to thank everyone that will be watching the video. And if you watch the video and you need clarification, okay, or if you get stuck with any concept, please feel free to reach out to me, okay? And my office hour will be conducted on Tuesday, 10 to 12, okay? So until next lecture that I'm actually going to come your way with another exciting topic, make sure you stay safe and protected, and bye for now.